Moin, moin. This is a very special paper about phase coupling. So I guess we have to start right at the beginning. Moin, what are oscillations?
Mm-hmm. Yeah, thank you very much for this opportunity. So, coming to our poster, I'm Moein Esghaei. I'm one of the authors of this poster. So here we discuss a specific feature of oscillations. First things first, when we talk about neural oscillations, we mean neural activities which are rhythmic, like the musical rhythms. They are rhythmic in the brain, across the whole brain. So this has been shown across all species, also all different brain areas. So when we look at the neural activity in specific brain areas, we see that the populations of neurons, or millions of neurons all together, they activate and deactivate, activate and deactivate. And this
is what we see in the EEG.
We see it in EEG, in electroencephalography, in MEG, and all sorts of field potential recordings. We also see it in single neuronal activities. I mean, when you target a single neuron, you could also see these oscillations at them. So this is a very ubiquitous property across the whole spectrum of species which have neurons, from Drosophilas up to apes and humans.
And when Berger found all this, and what we see in the EEG, there are delta waves when we are in deep sleep and theta waves, but there is a special, very special information about theta and beta. There's a correlation in there, isn't it?
Yes, exactly. That's quite right. So we have different frequency bands in these neural oscillations. And it's also very interesting that we have fingerprints. So some oscillations happen in some specific areas. So we know that, for instance, alpha oscillations happen a lot, as Hans Berger, back around a century ago, observed it first in the first EEG's recordings in Germany. And we see theta oscillations mostly in the hippocampus, which is mostly effective for memory formation and so on. So this is also very interesting. I mean, but as you also pointed out, we see ubiquitous theta oscillations across many brain areas, and at the same time, we see when we are in deep focus, like attending to a specific property in the environment, we see higher oscillations, higher frequency oscillations, as you pointed out, beta and even towards gamma oscillations. When we talk about beta, we mean frequencies around 15 to 25 hertz, 30 hertz, and when we talk about gamma, we mean frequencies around 30 hertz and above. So, but these high-frequency oscillations are a motif of activities of neural processings within specific columns of the brain, within very, very localized tissues. Whereas when we talk about low frequencies, theta and alpha and delta, as you pointed out, these frequencies represent activity across much wider brain tissue. Even different areas altogether generate these frequencies because they also have a much higher power. So it's been quite a while, around two decades or so, that people have been asking what's the interrelationship between low frequency oscillations and high frequency oscillations. And this here is where we come to coupling, phase amplitude coupling. So phase amplitude coupling, in very simple words, is the coupling between low frequency oscillations and high frequency oscillations. So if we start with a raw, this is a simulated data, but represents the neural activities in the brain. So when we start with the raw signals, it's made up of different frequencies. So if we filter it to high frequency oscillations and low frequency oscillations, by filtering we mean extracting the components which oscillate at high frequencies or at low frequencies. When we do this, we see that, interestingly, that high frequencies are locked to specific phases. Here, the peaks of the low frequency oscillation. And this has been observed. I mean, this is just an example, a theoretical example, which is coupled to the peaks. It might happen that it's locked to other phases of the low frequency. But this is really ubiquitously seen, observed across all species, across EEG, MEG, intracranial EEG, and LFTs, and so on. So, and there have been a lot of studies focusing and measuring this phase amplitude coupling across different tasks and behavioral tasks, across different disabilities. And it's been quite well observed that this PAC is linked to many specific brain functions: memory, attention, decision making, and so on. So it seems like it's very important. This is why we focused on phase amplitude coupling in this poster.
In your paper, you found out that there are varieties or special meanings. What is it?
Yes, exactly. Phase amplitude coupling in general can have two mechanistic meanings in the brain. The first meaning comes from the communication between areas. We know that areas should be talking to each other. Otherwise, when information comes in, the visual information comes into the occipital cortex, I mean, it can't do much at the level of occipital cortex, visual V1 and V2, unless it actually goes far beyond to the downstream areas and to the associative areas, where it gets converged with other modalities, auditory information, sensory information, and so on. I mean, we ultimately want to have a perception of a flying eagle, right? Something like this. So, one of the main roles of phase amplitude coupling is communication between areas. So this means that the two different areas, as I pointed out earlier, are very easily lockable through low frequency oscillations, because these low frequency oscillations are high power. They go across and beyond different columns of the neural tissue, so they can very easily synchronize to distinct and to distant brain areas. When this happens, then the gamma oscillations or the beta oscillations, high frequency oscillations, could have the chance of finding tightly linked time windows to start doing the actual communication between single neurons. So this is one of the main roles, which happens through phase synchronization. By phase synchronization of opposite of it phase dispersion, we mean that two different areas can lock to each other through low frequencies, and then when the gamma oscillations, gamma bursts or beta bursts, are locked to a specific or similar phase across the two brain areas, they have the chance of communicating with each other at the level of single neurons.
I have to ask, sorry.
Yes, sir.
Is this information?
So that's a good question. Information in the brain is encoded through high-frequency oscillations. Mm-hmm. Because these high-frequency oscillations are rhythms which are linked to single neuronal activities. I mean, this has been observed across many studies, that when we have gamma oscillations or beta oscillations, beta at the level of motor cortex, gamma at the level of visual cortex. So from now on, I'll talk about gamma. So people have observed that when neural activities at the level of single neurons start to process information, gamma oscillations start to also ramp up in terms of power. Mm-hmm. So these gamma oscillations are actually, I mean, about the neural substrate of it, they come from the interconnected activity of inhibitory and excitatory neurons altogether, which is a signature of localized information processing. So this is why whenever we see, very generally speaking, whenever we see gamma, it means there is some processing going on at the level of local neurons. So it's important to have a hypothesis that can tell us how these gamma oscillations or localized neural activities can start communicating across two areas. And phase amplitude coupling seems to be one of the very well established mechanisms which can describe this for us.
So we had phase dispersion. What about temporal dispersion?
Yeah, that's a very nice question. So that's what the main focus of our paper here is. People have been, in the literature, people have been mostly emphasizing on the role of inter-areal communication for phase amplitude coupling. What here we discussed was that phase amplitude coupling may also have another role, which is through temporal dispersion or temporal, or the opposite of it, temporal synchronization. This means that whenever we have high phase amplitude coupling, it means that gamma oscillations are linked to a specific phase like this. But in addition to this concept, we also have a presupposition that gammas happen in bursts. So meaning that they happen here, they don't happen the next window. Again, we have a gamma burst, and after that, we don't have any gamma burst. So this is a presupposition. So we have observed data, especially in monkeys and also humans, that this may not be always the case. So gamma bursts may sometimes invade, meaning that we don't have any gamma bursts like this, that in some time points we have no gamma and some points we have gamma. So this might change through temporal dispersion, meaning that gamma happens literally at all times. But the power of this gamma might differ. So in some points we have less gamma, in some points we have more gamma. Less gamma, more gamma. Or on the extreme side of the line, we could have gamma at all times. This might also happen. So what happens to the concept of phase amplitude coupling here? I mean, when bursting of gamma gets weaker, it means that we have gamma at all phases, at all phases of low frequency, so to say. And when this happens, we could say, okay, then if two areas want to get connected to each other, it doesn't make any sense that we have gamma at all places. So phase amplitude coupling here may not play any role. And this was the question. So we came up to a new mechanism, hypothetical mechanism, which we have shown in the last 10 years in our publications, that this might be a new mechanism through which a single area might start synchronizing or desynchronizing neurons at the local level. So in other words, when we have gamma bursts, this means that there are very localized and short time windows where all neurons, most of the neurons, are obliged to fire in these windows. So meaning that these neurons are obliged to synchronize together because they fire together. And in those time windows where we don't have any gamma, neurons are obliged not to fire, so they don't fire together. So this is an indirect way for a neural network to synchronize or desynchronize neurons. And what happens when we don't have any PAC, or we have a low PAC in this case? Then neurons start to fire at all places, at all times. Okay. So we come up with a complete desynchronization. It's very much like what happens in an orchestra. When we have the conductor starts to synchronize different groups together. When we don't have any conductor, just imagine what happens. Yes. Anybody, playing his or her own tone. So we have two different dilemmas, two different themes where PAC may play a role. In the phase synchronization or phase dispersion theme, phase amplitude coupling plays a role in communicating between areas. And in the temporal dispersion or temporal synchronization theme, the neural network and PAC tries to synchronize or desynchronize neurons in a single area. So one has a role in interconnection between areas, the other has a role in modulating the neural processing capacities of a single area. So this is the main distinction we try to create in this poster, because previously when people talk about PAC, they used to say, okay, PAC is enhanced, PAC is suppressed. Nobody cares what happens for the PAC to get suppressed or enhanced. Is it, and this is why people, the literature had, contrasting results. Some people observed high PAC with a faster behavioral response, which is a signature of faster information transfer, and some people observed the opposite, lower PAC with an enhancement of behavior. So the literature was kind of, not sure what's actually happening. So here we try to solve that kind of dilemma, this kind of contradiction in the literature by suggesting that people should, and scientists may want to look into different measurements of phase amplitude coupling. And the remaining of the poster, which becomes more quantification based, we try to establish our new approach to measure phase dispersion versus temporal dispersion.
This sounds like very important work, but just a start, isn't it?
Exactly, that's true. That's true. We are actually in this paper, in this poster, which we already also posed the main ideas in a recent paper published by Cell. We tried to put the set the pave the way to actually ask the scientific community, systems neuroscientists mainly, to start thinking about subsections or subtypes of phase amplitude coupling, in contrast to measuring phase amplitude coupling in a very general way and try to interpret it that way. But we just don't propose this. We also give a quantification basis for this, where we actually introduce two different measurement factors. One is the TBI, which is the temporal burst index for measuring the extent to which gammas happen in bursts or not in bursts. And on the other hand, we suggest phase dispersion in using circular variance of the gammas, which would tell us how much variance in terms of the coupled phase gammas would have. So the first one would be representative of the temporal dispersion, would quantify temporal dispersion. The second measure would quantify for us phase dispersion. And then using these two factors, we showed in our simulation analysis that we can see a very distinct measurement when we created data which were time concentrated or time dispersed.
Okay. Different way to look at it.
Yeah, exactly.
Wow. Thank you very much.
My honor. Thank you very much for giving me this chance to talk about our research to your audience.